Good morning. Today we will study about lattice energy of ionic crystals. The stability of ionic crystals is determined in terms of their lattice energy. Lattice energy is defined as it is the amount of energy released when 1 mole of ionic crystal is formed from its constituent ions in gaseous state. That is, when 1 mole of a ionic crystal, for example 1 mole of NaCl, is formed from its constituent ions, that is sodium ions and chloride ions, in the gaseous state, then the amount of energy released is known as lattice energy. And the formation of 1 mole of ionic solid from its constituent gaseous ion, it may be represented as M plus X minus in the gaseous state, and they form Mx, and then the energy released, that is delta H, is known as lattice energy, and lattice energy is expressed by the letter capital U, and the negative sign is used because energy is released in the process. Therefore delta H is minus U. Since ionic bond is formed as a consequence of electrostatic attractions between the oppositely charged ion, there is considerable decrease of potential energy of the system, and as a result, if 1 mole of a solid ionic compound is broken into its constituent gaseous ions, energy will be needed, which is numerically equal to the lattice energy. That is, when 1 mole of Mx is broken down into its constituent ions, that is M plus and X minus, then the energy which is needed, that is delta H, is equal to plus U. In this case, U has positive sign because energy is absorbed in the process, and it is obvious that if the compound is stable, a large amount of energy will be needed, because numerically it is equal to lattice energy. This means that the higher the lattice energy of an ionic compound, greater will be its stability. And lattice energies of some compounds are given in the table. Ionic solids such as LiF, it has lattice energy minus 1033, cesium fluoride has minus 748, sodium chloride has minus 778, and lithium iodide has minus 140, cesium iodide has minus 601, and so on. Then from the table, it is obvious that the lattice energy of ionic solids are quite high, and this is because of the strong electrostatic forces of attraction between the oppositely charged ions present in the solid. Since Coulombic forces of attraction vary directly as the product of charges, it follows that higher the valency, that is charges of the ions, greater will be lattice energy of the ionic solids. Thus lattice energy increase as we move from univalent ionic solids to bivalent ionic solids, and then to bivalent ionic solids. That is, greater the charge, then greater would be the lattice energy, and lattice energy increase as the charges increase. Then the Boron-Haber cycle for lattice energies. Boron and Haber in 1919 proposed a method to relate the lattice energy of an ionic crystal to other thermodynamic data, and this is known as Boron-Haber cycle. And we have learned that the formation of bond takes place only if there is decrease in energy. As an example, Consider the energy changes during the formation of sodium chloride from metallic sodium and chlorine gas and formation of a Boron-Haber cycle, that is sodium in the solid state plus half Cl2 NaCl is formed. And the total process, that is overall process, is thought to takes place in the following steps. In first step, there is conversion of metallic sodium into gaseous sodium atoms. That is, sodium atom can lose its electrons only in the gaseous state and has to be sublimated. The energy required for the conversion of 1 mole of metallic sodium into gaseous sodium is called sublimation energy, and it is represented by capital S. That is, sodium in the solid state when energy, that is sublimation energy, is conversion of metallic sodium into gaseous sodium atoms. Sodium in the solid state plus sublimation energy, that is sodium is converted into gaseous state plus energy, that is known as the sublimation energy. Then second step is dissociation of chlorine molecules. Dissociation of chlorine molecules into chlorine atom, and it is shown in the table, and that is a chlorine molecule consists of 2 atoms of chlorine. The amount of energy required for the conversion of gaseous chlorine molecule into atoms is known as dissociation energy, and that is Cl2, half Cl2 plus dissociation energy half, because for producing 1 mole of gaseous chlorine atom is d/2. Then chlorine is converted into chlorine in the gaseous state. Then third step is conversion of gaseous sodium atoms into sodium ions. That is, amount of energy required to convert 1 mole of gaseous sodium atoms into sodium ion in the gaseous state is known as ionization energy, and it is denoted by IE. That is, sodium in the gaseous state plus energy is given, that is ionization energy. Then it is converted into Na plus and 1 electron is released. Then the next step is conversion of gaseous chlorine atoms into gaseous chloride ions. This is the amount of energy released during the conversion of 1 mole of gaseous chlorine atoms into chloride ion, and it is known as electron affinity. Chlorine in the gaseous state plus energy is applied, then chloride ion plus electron affinity. Then there is combination of oppositively charged ion to form a solid crystal, that is oppositively charged ion Na plus ion and chloride ions attract each other to form a NaCl crystal, and this leads to the release of energy. And the amount of energy released when 1 mole of solid crystalline compound is obtained from gaseous ions of the opposite charge is called lattice energy, and it is denoted by U0. That is Na plus in the gaseous state plus chloride ions, then we get NaCl in the solid state plus energy, and this energy is known as lattice energy. And the overall energy change, it may be represented as, that is Na in the solid state plus half Cl2 in the gaseous state, and NaCl is formed. And the heat change for this reaction is called heat of formation, and it is denoted by delta HF. And the various steps, they may be represented in the form of Boron-Haber cycle as shown in the figure, and according to the Hess's law, the heat of formation of 1 mole of sodium chloride should be the same irrespective of the fact whether it takes place directly in one step or through a number of steps, as shown in, that is delta F is equal to S, that is sublimation energy plus dissociation energy plus ionization energy plus electron affinity plus lattice energy. And when we calculate the lattice energy, then lattice energy U0, that is equal to delta HF minus S minus half ID, that is dissociation energy, minus ionization energy minus electron affinity, as shown in the figure, that is Bohren-Haber cycle for the formation of NaCl. And this lattice energy, it can be calculated by knowing the values of different quantities. And while using the above relation for the lattice energy, a special care that should be taken for the signs of various quantities. That is, positive sign is used for energies absorbed and negative sign is used for energies released. As we can see from the example, that is, calculate the lattice energy of NaCl crystal from the following data by the use of Bohren-Haber cycle. That is, sublimation energy of sodium is given, dissociation energy of Cl2 is given, ionization energy of sodium is given, and electron affinity of chlorine is given, and heat of formation delta HF is given. Then how we can solve? That is, solution U0 is equal to delta HF minus S minus half D minus ionization energy minus electron affinity, and we put all these values. As all these values are given, then we can calculate U0, and its unit, because it is the energy units, are kilojoule per mole. That is, lattice energy of NaCl crystals is minus 773.95 kilojoule per mole. Then there is application of Bohren-Haber cycle. What are the applications of Bohren-Haber cycles? First, the application of Bohren-Haber cycle is that it has been used for the calculation of many properties. Some of the important uses, they are: first is calculation of the heat of formation, that is delta HF, as we have already studied that by making a Bohren-Haber cycle, the heat of formation of unknown compounds can be calculated. That is, delta HF is equal to S plus half D plus ionization energy plus electron affinity plus lattice energy. Then we can calculate delta HF, that is heat of formation, and the heat of formation tells us about the stability of the compound. That is, if the heat of formation comes out to be negative, that the reaction is exothermic, that is, the compound formed will be stable. And if the heat of formation comes out to be positive, then that is, the reaction is endothermic, that is, formation of the compound will be highly unfavorable energetically. And from heat of formation, it can be explained why NaCl2 is not formed, though it is expected to have higher lattice energy than NaCl. And the heat of formation for NaCl2 by using Bohren-Haber cycle, it comes out to be highly positive. So NaCl2 cannot be formed. Then second use is calculation of the electron affinities. The Bohren-Haber cycle can be used for the calculation of electron affinities of some elements which are otherwise very difficult to measure. And heat of formation of a compound as expressed, that is delta HF is equal to S plus half D plus ionization energy plus electron affinity plus lattice energy, and electron affinity can be calculated from here, that is electron affinity is equal to delta HF minus S minus D minus ionization energy minus lattice energy. If the values of S HFD and ionization energies are experimentally determined, and lattice energy U0 may be calculated by using the Bohren-Haber cycle, and using the above equation, electron affinity can be calculated. Then the third use is estimation of proton affinities. That is, Bohren-Haber cycle can also be used to calculate the proton affinities of different bases. The proton affinities of a species is defined as the energy released in the reaction, that is X plus H plus gas state, then HX plus is formed. For example, the proton affinity for ammonia, it may be expressed as NH3 plus H plus, that is NH4 plus ion is formed, then delta H, that is equal to proton affinity. And this can be easily calculated by considering the Bohren-Haber cycle, that is NH3 plus HCl, and delta H of heat of formation is equal to NH4 plus Cl. And by using different steps, that is NH3 gaseous state plus HCl, HCl is dissociated into H and Cl, then ionization energy, H plus ion is formed. From electron affinity, chloride ions are formed, and when proton affinity, that is NH3 accept H plus ion, that NH4 plus ions are formed, and chloride ion, and by energy is released, that is lattice energy is released, then NH4Cl is formed. And knowing the values of all these, that is delta H, D, ionization energy, electron affinity U0, we can easily calculate proton affinity Pa. For the reaction of NH3 and HCl, the lattice delta HF is minus 144.5, lattice energy minus 648.5, ionization energy is 1311.6 kilojoule per mole, electron affinity minus 347.2 kilojoule, and dissociation energy is 430.9 kilojoule. And substituting the values, we get proton affinity is equal to minus 891.3 kilojoule. Thus, this is the proton affinity for ammonia, and negative value indicate that the reaction is favorable, and therefore ammonia has good tendency to accept the protons. Thank you. Have a nice day.